So I was thinking about how to give this talk, and when Irina sent me the invitation, she mentioned there'd be pretty lots of different people in the audience, students, public, and so forth. And whenever I see that it's just, it's not a typical colloquium, especially public is involved, it makes me realize that there may be people here against their will. They're here because they're attached to someone who wanted to come, and they just go in to support them. So I'm going to do my best to try to make the talk accessible to everyone, including those people, because I understand what that's like. I thought I'd start this journey by telling you about a pilgrimage of sorts, something I took. It's been a while now. It's been 15 years ago. I took this journey to the American Southwest, into the starkly beautiful state of New Mexico. And I had never been there before. And the nearest town to where I was ultimately headed was right about here, and it was Santa Fe, New Mexico. That's not where I was ultimately going to go, but I stopped in, and I was shocked to find out that I already owned a blacksmith shop. This is my name, and there I am under my blacksmith shop, and that's me 15 years ago. And given that I clearly had already established myself in Santa Fe, New Mexico, I was really shocked at just how unsuccessful I was at blending in with the local culture there. But that's okay. That's not why I came. Rather, it was to drive along some muddy dirt roads with only some cows looking at me once in a while, come into this serene landscape, and then ultimately arriving at the most remote national park in the continental United States. Have any of you ever been to Chaco Canyon? See how remote it is? We're not even that far away. Now, when I did this is when I was actually in Massachusetts. It was a long trip to get here. And the whole reason I came here wasn't the reason that 99 out of 100 people go to Chaco Canyon, which is to see the most well-preserved ruins of any Native American society. About 1,000 years ago, Native Americans known as the Anasazi people flourished here, and they left us these ruins, which were remarkably well-preserved, considering that there was absolutely nothing stopping you from climbing all over them, and people were doing that. So I did too. Okay, but it just seemed odd. But anyway, very interesting structures. It was clearly a people that were in tune with their environment. A lot of the buildings were right on cardinal east-west axes and so forth. But I zipped past all this. Instead, I walked for about an hour on some not very well-marked trails until I came to this rather unassuming cliff face where it was discovered in the 1950s that if you walk down to here and look up on the underside of a ledge that is now about 25 feet above the canyon floor, you see this. You don't have to be an astronomer to realize basically what you're looking at. This is a pictograph, very well preserved on the underside of this ledge. It's been dated to about the 11th century AD, and it's clearly a hand. There's a crescent moon, and anyone who's ever been in first grade knows that this is the universal symbol of a fiery object right there. 1,000 years ago, they do it the same way we do today. Turns out, this pictograph, as it's called, is extremely interesting, especially if you come at just the right time. About every 18 and a half years, if you stand right under this ledge and look out past the ledge into the patch of sky indicated by the direction of the fingers of the hand, there will be a crescent moon, a moon in just that phase, and if at that time you look off to the side at the spot in the sky indicated by the fiery object, and you happen to have brought a nice telescope with you, you will see this. This is not what you see when you point your telescope randomly in the sky. What on earth is this? You're looking at what remains after one of the most violent events that can occur in our universe. About 1,000 years ago, a star exploded. and it gave quite a cosmic display for all the inhabitants of the Earth. It wasn't just the Anasazi people that saw it. It was noted by cultures all around the globe. Imagine a star just explodes. What the people of the time saw was that suddenly there was an enormously bright star in the sky that hadn't been there before. We now know there was a star. It was just pretty faint. But when it exploded, it became so bright that it was visible in the daytime for several months. And it was visible in the nighttime sky for many years before it faded down to the point where now you need a telescope to see what remains of this. If you're wondering what the ancient people might have seen, this is a recreation of what it might have looked like from the original Cosmos series.
Imagine the night when that colossal stellar explosion first burst forth.
A 1,000 years ago, people gazed up in amazement at the brilliant new star and wondered what it was. We are the first generation privileged to know the answer. Through the telescope, we have seen what lies today at the spot in the sky noted by the ancient astronomers, a great luminous cloud, the remains of a star violently unraveling itself back into interstellar space.
So I know what you're thinking. Wow, I'd love to see one of those. And then maybe I too would be inspired to put some graffiti on the underside of a ledge. Unfortunately, it's a very rare star that does this. Best we can tell, about 1 out of every 400 stars that nature produces ends its life in such a dramatic fashion. And though there are many, many stars that you can see in the night sky, they only end their lives once. And so getting one to explode that is so nearby you can study it like that one is very rare. And in fact, the last one that was so close that it got everyone's attention like that, it was so bright, was about 400 years ago, in the time of Johannes Kepler. I sometimes think nature took note that we invented the telescope in 1608 and gave us the last naked eye supernova in 1604 and said, oh great, you invented a telescope, now you're going to need it to see any other exploding stars. So we haven't had one in a long time. Because in order to get one that's so close that it's just gets everyone's attention, it has to be really nearby, near our home. So let me try to explain where our home is. This is the best we understand our home. The Milky Way galaxy. Our sun is not alone in space. It actually travels through space along with about 100 billion other stars that are all bound together into a vast conglomeration that we call the Milky Way galaxy. Our sun sits out somewhere around here, okay? And it takes about 250 million years for our sun to orbit the center of our galaxy one time. So you might call that a galactic year. And so when I say we're looking for a star to explode nearby, what I kind of mean is like if you take that to be our sun, it's got to be kind of in a circle or a sphere surrounding us like that. It's got to be in our part of this galaxy. And the last one was in 1604. That was that close by. Let me give you a little sense of scale here. You've probably noticed this is not a picture. This is an artist's idea of what our galaxy might look like if we could ever get far enough away from it to turn around and actually take a picture of it. We're not even close to being able to do that. So we have to hire artists to make pictures of what we think our galaxy would look like if we could get out of it. Let me give you a sense of just how vast this system is. And I'm going to do it in terms of the length of time it takes light to get from one place to another. So let's start really close to home with a very familiar object. We've never named it. We just call it the moon. It's kind of curious. It doesn't really have a name because we call moons of other planets special names. Ours we just say is the moon. I always thought that was kind of funny. But this is the closest astronomical object to us, and it is the only place we've actually set foot. It's the only place we've gone, And we see it because the light coming from our sun bounces off it and reflects off it and comes to us. The moon is about 200,000 miles away, and it turns out that's about how far light travels each second. So what that means is when you look at the moon, you're seeing the light that bounced off it 1 second ago. And another way of thinking about that is you're looking back in time 1 second. You're always seeing the moon in the past, about 1 second. The sun, you're seeing the sun, this self-luminous hot ball of gas giving off its own light. It's about 500 times further away from us than the moon, so if you do the math, you find out that it takes the sun's light about 8 minutes to reach us. So you might say the sun's 8 light minutes away from us in distance. Our astronomers have learned that our sun is essentially exactly like all the stars that you see at night. It's just so much closer that it's so bright that you can't see the other stars when it is out, and that's what the daytime is. And then when it sets, we see all the other stars. But those are just suns that are just so much further away. And they're way further away than the sun. This is a picture of the closest star other than the sun to us, and its name is Alpha Centauri. There it is. And it takes light from Alpha Centauri 4 years to reach us. So you might say the nearest star to us is 4 light years away. When we return back to this whole collection of stars, this gravitationally bound object we call the Milky Way galaxy, you can see why we've never traveled outside this thing to get a picture of it. From end to end, the Milky Way galaxy is about 100,000 light years across, and we sit out here about 30,000 light years from the center. We've launched spacecraft. The spacecraft have explored planets, Pluto even, the dwarf planet Pluto, I guess we'll say. But if you're thinking that, well, that spacecraft's really cruising, it is. It's going very fast. And the other spacecraft that we've launched way back in the 1970s, the Voyager spacecraft, they're going very fast. And after traveling for 40 years or so, they're not even 1 light day away from us. So 30,000 light years to the center, the fastest thing humans have ever sent away is still within a light day of us. So we're not close to actually having a nice picture from outside our galaxy. On the other hand, we can take awesome pictures from our perch in the outskirts of our galaxy of other galaxies. We're not the only galaxy in the universe. Here is a picture of the closest major galaxy to us. It's about 2 million light years away. And this is a picture that kind of looks like what your eye could see. You can actually see this thing with your unaided eye. It looks kind of like that. It's this fuzzy thing. And people are often confused about what they're looking at in pictures like this. These little dots, these are stars in the Milky Way, maybe 10, 100 light years away. This fuzz is the combined light of 100 billion stars 2 million light years away. So you're looking through a screen of stars that are in front of you. That is Andromeda. And we do have better pictures of it. I'm going to show you a picture taken by an amateur astronomer using his own telescope. And that's the closest major galaxy to the Milky Way. We probably look something like that galaxy. We see billions of galaxies. Let me show you some pretty pictures. Love this galaxy. This is a beautiful picture too. And this wasn't taken by any ground-based telescope. This was taken with the Hubble Space Telescope, and I'm going to be showing a lot of pictures taken with this telescope. And the reason is that this telescope isn't sitting on Earth's surface, it's orbiting the Earth once every 90 minutes. And the reason we did that was that puts it above our atmosphere, and the atmosphere is great for human life, terrible for astronomy. So we like to put our telescopes out above the atmosphere so they get unobscured views of the universe. And our crispest, just most dramatic pictures, and the ones that are just the highest resolution images we've ever taken have been taken with the Hubble Space Telescope. Let me show you some more pictures that the Hubble's returned to us. This is another galaxy. So you're looking at, again, about 100 billion stars or so. Here's another one. Love that galaxy. So 100 billion stars. About 1 out of every 400 that is ever born dies by exploding. And that might not sound like a lot, but remember, when you're talking 100 billion stars in a typical galaxy like this, if you start working out the odds of how often there should be an explosion, a so-called supernova, you find out roughly 1 per century. Bad project for a graduate student, to stare at one galaxy and hope there's an exploding star in it. Might get lucky. On the other hand, if you look at thousands of galaxies, you increase your odds considerably. And we're now at the point where we discover many, upwards of 1,000 supernovas per year. So let me show you a picture of a galaxy right here. This is a famous galaxy. It's called the Whirlpool Galaxy, and it's about 23 million light years away, making it a really close galaxy. It sounds far, but this is in our backyard. Okay, this is a really close one. And I want to show you what an exploding star looks like when it occurs not in the Milky Way, but when it occurs in another galaxy, because this is where we discover all of our supernovas right now. So again, what you're looking at here, this is the smeared light of 100 billion stars. These are Milky Way stars. We don't care about those. They're just in the way. Okay, they're close by. This is the thing of interest. So here's a picture of this galaxy in 2011, minding its own business. And then one day, one of its stars decided to end its life by exploding. So you can consider this the before picture. That's what a supernova looks like. That certainly doesn't inspire you to put graffiti on the underside of a ledge unless you're an astronomer, right? But just think, that one star, 23 million light years away, is as bright as this guy. I don't know how far away he is, maybe 10 light years, okay? They're such powerful luminous things that you can see them across the universe. So it's been over 400, 500 years since we got one of these things right in our own neck of the woods. But it seems like if you want to watch stars die, your best bet is to look at other galaxies. That said, if you want to see the next great supernova in the Milky Way galaxy, really close to us, I can tell you right where to look. The star I'm going to tell you to look at is in this picture. This is the constellation of Orion the Hunter. People with pretty good imagination see a belt here, a shoulder, and an arrow quiver here. Anyway, I never see these things, but it's called Orion the Hunter. And there's one star in there. It's huge in size. It's also big in mass. It has about 20 times the mass that our sun does. So it's a gargantuan star. And it's, in terms of how bright it is too, it's extremely luminous. It's about giving off the light of about 100,000 suns. So it's a really, really luminous star. We wouldn't want it to be replacing the sun right now. This is a picture taken for a totally different reason, right? They didn't know it was going to explode, but it happened to be at the right spot. And when they line up, and notice these pictures are taken at different filters, different wavelengths. This one's in color, this one's in black and white. Okay, so there are differences, and the resolutions are different. This one's higher resolution, but like that star there is that star, that star is that star. Those two are those two. And this guy, see that little star right there? Right next to the supernova? That star is that, and that is the star that lines up with the supernova. And those two stars there are kind of blurred together as that lump right there in that picture. See, this picture isn't as high quality because they didn't know it was going to be this important when they took it. They took it for some other reason. But that is the star that now sits where the supernova is. And it looks exactly like Betelgeuse. You can just tell by the color. But you can do even more. You work it out. It's 100,000 times the luminosity of the sun. It's one of these red supergiants exactly like Betelgeuse. And that's why we watch Betelgeuse to see when it's going to explode. Now, scientists are always very skeptical. And if all you had was this before picture, and you said, it's the star that exploded, people are going to say, I want to see proof that that star blew up. And so what proof consists of is being very, very patient and waiting for the supernova to just fade away. It takes a couple of years till it fades down beyond the detectable limit. And what you really want to do is get another picture, and that star better not still be sitting there. Because if it is, it didn't explode. So I'm going to show you the after picture over here, and it's gone. It blew up. That's the before, that's the supernova, and that's after. And we have pictures like this now for 10, 12 or so. It's pretty rare that you get that nice before picture. Stars. And in every case, for the kind of explosion this was, it's a red supergiant sitting there. So we know Betelgeuse is going to do this one day. We just don't know exactly when it's going to be. We know it's coming. Okay. And this is the kind of work I do. You can kind of consider it like stellar forensics. The star explodes, and then you're interested in it. And then you kind of go back into the archives to see, did someone take a picture of this before? What can we learn about the star that eventually exploded? So let me say a bit about our uncertainty. Why can't I tell you Betelgeuse is going to explode on October 3rd, 2019? Why do I have to say sometime in the next million years? The reason we can't tell you if it's going to explode tomorrow, or whether it's going to wait a million years, is that everything that determines whether it's going to when it's going to explode is buried in the core of the star. It's not the surface of the star. You want to see into the core of the star, and we haven't yet figured out how to do that for a star that's 500 light years away. So let me tell you a little bit about what's going on inside these stars and why it's what's happening in the core that determines whether it's going to explode. So I already said a star is just a big ball of gas, big ball of hot gas. And if you think about it, it's kind of weird that a star is even puffy, right? Because you all know about gravity, right? Gravity is the thing that pulls everything to the center of a massive object. Earth has gravity. Gravity would love to just crush the Earth into nothing, but it can't. Because Earth's made out of heavy stuff like iron and stuff, and it has chemical bonds and stuff, and it resists being crushed any further than it already is. But a star is just a big puffy gas, so you have to ask, why isn't the star just collapsing? Gravity would love to just pull the star all together. And the answer has to be that in addition to gravity pulling it in, there has to be pressure pushing out. And those two things have to be in a perfect balance to keep the star just the way it is. And the trick is, when a star is actually alive, which means it's producing its own energy and its own light, that is actually the source of the pressure that pushes out against the rest of the star. And the generator of all that energy is in the very center of the star. The fuel in the center of a star is the simplest element in the universe, and also the most abundant one. It's hydrogen. We've figured it out. Stars are able to shine with all the might that they do because they are taking hydrogen atoms in their core, and here's your periodic table of the elements. Hydrogen sits up here, it has one proton, okay? And what we've discovered is that the centers of stars are so incredibly hot that hydrogen nuclei, each of which is one proton, that's all we're saying when we say a hydrogen nucleus, ordinarily, if you send two protons towards each other, they don't like to be anywhere close to each other because they're both positively charged and they feel this repulsive force called the electric repulsive force. But in the centers of stars, the temperatures are so hot, tens of millions of degrees, that the atoms, the nuclei, are moving so fast that once in a while, two protons make a head-on collision and they get so close to each other that they stick together before they get driven apart by the electric repulsion. And a really weird thing happens. If you take two protons and you jam them together, and then you jam another proton on, and you jam another proton on, it creates a new element, because it's more protons in the nucleus. But the really weird thing that happens is it also releases energy. You know the very famous formula, E equals mc squared? A little bit of the mass of the hydrogen nuclei get converted into energy through this extraordinary process that we call nuclear fusion. And that is the light that is produced from the cores of the stars, and that light actually pushes against the envelope as it gets its way out, all the way out, and then finally flies off of the surface. But as long as there's nuclear fusion happening in the core of the star, it keeps the star puffed up. It balances gravity. The problem for stars, all stars, is that, like a car, it eventually will run out of gas. It's going to run out of fuel. There's a lot of fuel in the centers of stars, but it doesn't last forever. And hydrogen can fuse into helium, the next heavier element. Helium can fuse into carbon and oxygen, and so on. Okay? But in order to fuse these heavier elements, you need higher temperatures because there's more electric repulsion, because those nuclei have more protons. So there's more repulsive force. So temperatures have to get higher and higher and higher. It gets harder and harder. All right? Our sun, let's use it as the example before we move on and talk about Betelgeuse. Our sun is it's currently fusing hydrogen into helium. It will be able to fuse helium into carbon and oxygen, but it ain't going to be able to fuse anything heavier than that because the temperatures in the centers of a star like the sun never get high enough to fuse elements with so many protons in their nuclei. So if you're wondering what's going to happen to our sun when it runs out of fuel, and by fuel I mean anything able to be fused in the core, first, don't worry about this. 4.5 billion years from now. It's got a lot left in the tank. But at that time, what will actually happen is our sun, its core, will begin shrinking down, and it will actually push off about half of its mass into interstellar space. And it'll be a beautiful thing. You won't want to live there anymore, but maybe by 4.5 billion years, we'll colonize a planet around another star, and we can gaze back at the sun and watch this beautiful phenomenon where this is not an explosion. There's a dying star in the center, and it's pushed off its outer envelope, and it's just floating away into interstellar space. And this is a big object here. This is about a light year across. So it's just, boom. This is how stars like our sun will end. And this thing in the center, if you're curious, it's basically like a little fossil of the old sun. It's basically a little nub. It's like the size of the Earth, which is big to you and me, but compared to the sun, it's about 1/1,000,000th the size. And it's made out of carbon and oxygen. And it's just a little cinder. It's not producing any more energy of its own. It's just cooling off for the rest of time. It's something known as a white dwarf. And that's what's going to happen to our sun. And it's the fate of 399 out of every 400 stars. That's the ending for the vast majority of stars. But nowhere in that description was there an explosion. And we're here to talk about explosions. So we have to make a few points here. Okay? Point number one, even for those stars like our sun, this process of fusing the heavier elements, if you look at the properties the core has at those times, it's getting hotter and hotter and hotter and hotter. Which means the actual rate of fusion goes way up as the star ages. And there's a point near the end of the life of stars like our sun where that nice balance between gravity in and pressure out is won by the pressure out. And actually the star becomes this big bloated star, kind of a gargantuan giant of its once much smaller self. Our sun will do this. It will puff way up in its later stages of life and almost, we think, swallow the Earth. It'll swallow Mercury and Venus and almost the Earth. And it puffs up. And that stage is what's called the giant stage. And it indicates a star that's nearing the end of its life. Really heavy stars, though, ones that are way more massive than our sun, puff even further up. And since astronomers are very creative people, we call that kind of a star a supergiant instead of just a giant. All right? And these stars, these really massive stars, and when I say really massive, I mean probably they have to be born with more than about 8 times the mass that our sun was. And that's very rare. Maybe 1 out of 400 stars is born like that. When they swell up, they become the size of Betelgeuse. And they'll be able to fuse heavier and heavier elements in their cores all the way up to this element here, Fe. That's 26 protons, and of course Fe stands for iron. Makes a lot of sense, right, in English. But when those really high mass stars, capable of fusing elements all the way up to iron, incredibly hot temperatures in their cores, billions of degrees, there's a problem because even they run out of material that they can fuse because physics says iron is the end of the line. You don't get energy out of fusing elements heavier than iron. It's just the laws of physics. And so even these really high mass stars, if you probe into their cores, you see progressively heavier and heavier elements. You always end up in the middle eventually with an iron core, which is no good to anyone because it can't get more energy out by fusing. So the problem with Betelgeuse is we don't know what stage it's in. It could be just helium fusing into carbon and oxygen, in which case it has maybe another million years left. If it's forming an iron core, it's going to explode tomorrow because that last stage is very, very, very fast. And here's what we think happens. After a star has fused all these really, really heavy elements and you wind up with this iron core, it's a horrendous situation because gravity starts to squeeze the core, but no more fusion can happen. And so gravity is going to win this time. And what happens is when this core gets massive enough, maybe 1.5 times the mass of our sun or so, there's so much gravity that the core basically just implodes. And implodes in less than a second. From something that might have been about the size of the Earth down to something about the size of the city of San Diego. And really weird nuclear physics happens in this collapse. Essentially, all of the protons and electrons that were in the core get squeezed together to form neutrons. That's weird. You don't see that happen every day. And what you're left with in the center is a ball of neutrons about the size of a city in a catastrophic collapse with speeds approaching a quarter the speed of light for the material. This happens in less than a second. The iron core collapses from Earth size down to San Diego size. What happens next? I always think of what happens next in relation to an old cartoon called Roadrunner. And most of you probably have seen this. It's, I don't think my kids have ever seen the Roadrunner, so I'm going to have to stop using this analogy at some point. But if you remember the Roadrunner would always run, and then there was Wile E. Coyote following the Roadrunner, and the Roadrunner always did things like there was a cliff here, and the Roadrunner would zip like this, and the Wile E. Coyote would run off the edge. And what always happened? He would run off the edge, and then this doesn't happen in real life. He stands there for a second, and then he looks down and sees nothing's holding him up, and he falls, right? And then poof, there's smoke. Anyway, this is how I think about what just happened. The core of this high mass star was the thing holding the star up. And it just went down to this tiny little thing, this ball of neutrons. And the rest of the star looks down like Wile E. Coyote and says, nothing's supporting me anymore. And so it implodes. So the core collapses and the rest of the star implodes on top of that core. And the rest of the star, which you can call the envelope of the star, smashes into this ball of neutrons. We actually call this ball of neutrons a neutron star. Good name. And it smashes into it, and that forms a shock wave that travels out through all the infalling material and ejects it out into interstellar space, and that is the birth of a supernova. The rare star, 1 out of 400, that ends its life in such a dramatic fashion. All right, let me also pause and just say, it's really good that stars do this. It's really good that there's such things as supernovae in the universe. Our universe did not begin with any carbon or oxygen or iron in it. It began with just hydrogen and helium. That was it. And if you look at what makes up you and me and our planet, it's not just hydrogen and helium. We're made out of carbon and oxygen. If the universe didn't A, find a way to manufacture those elements, and then B, find a way to disperse them out into space to form new things, you wouldn't exist. So you wouldn't be here if stars didn't explode. So, wow. All right, so this all sounds quite nice. Stars explode. We even know which kind of stars explode. There's observational proof. Okay? We see things like this. All right? The reason it's so rare that we really can nail down the so-called progenitor star, that is the star that explodes as a supernova, is pretty as this picture is, it ain't at all useful for this work. In this picture, you cannot identify the progenitor star of that supernova. It's not sharp enough. The detail isn't there. The resolution isn't there. You have to be very lucky, or someone had to have been very prescient, to have taken a really high resolution photograph of that part of this galaxy so that you can then study the progenitor star of a supernova. And by really high resolution, what I usually mean is it has to be a picture that the Hubble Space Telescope has taken. And the Hubble Space Telescope's been taking pictures for a long time, and they maintain an archive of all the pictures that they've ever taken for any reason. And it's only in those pictures, and the supernova has to be within 20 million light years or so, for you to be able to really pick out individual stars, even with the highest resolution pictures. Let me give you an example of a picture taken with the Hubble Space Telescope. This is my favorite galaxy in the universe. It's called NGC 1637. Love this galaxy. Have stared at it more than any other galaxy. It's about 13 million light years away. And it's my favorite galaxy because for a totally different reason. The Hubble Space Telescope let me point at this galaxy and take pictures for about 18 hours. It was for a totally different project. It wasn't about supernovas. And so I created this beautiful picture, I think, of this galaxy using the Hubble Space Telescope. That's it. That's the shape of the camera. Okay, I didn't do that to it. But what's amazing about this is you can count, and I did because I was a postdoc at the time. Now I get a student to do this. You can count tens of thousands. I think the final number is 80,000 or so of the brightest stars. They're all resolved in this image. If a supernova were to explode in this galaxy, this picture would be very famous because then everyone would go back to it and they would care a lot about it. All right? And so this is the trick. You need to have had someone, for some reason, take a picture of your galaxy that happens to have had a supernova go off in it. All right? And we found by studies like this that Betelgeuse and stars just like it are the kind of star that generally explode. On the other hand, there have been surprises, and I'm going to tell you about a personal journey of surprise that I took some years ago in this game. Not everything we've seen has conformed with our expectations. So let me tell you about the shocking case of Supernova 2005 GL. Okay, looks like a good self-respecting supernova. The arrows always point out where they are. It's amazing, these pictures come with arrows. That's it right there. Okay, that's the supernova in this galaxy right here. The thing is that the progenitor, the star that gave rise to this supernova, turned out to be nothing like the others that we had seen. And so let me tell you a little bit just about this. So this is, I'm going to show you, everything I show you from now on is going to be an extreme close-up. It's like I can't even draw the square small enough to indicate the region around the supernova. And these are all pictures taken with the Hubble Space Telescope. Okay? So there's your galaxy and the supernova. This is extreme close-up of the supernova while it was really bright. We asked the Hubble Space Telescope, please take a picture of the supernova. And it did. And this big blah here, black means bright in these images, it's a negative image. That's the star, that's the supernova. Unresolved, it's a point source, all right? But even with the resolution of the Hubble Space Telescope, it's very pixelated. And these other things here, that's a star as well, all right? And it turned out that 8 years before that explosion, different astronomer had taken a picture of that same patch of sky for a totally different reason. And after Supernova 2005 GL went off, my colleague Avishai Galyam and I went back to the Hubble Space Telescope archives and dug up this picture. And this is kind of a picture only an astronomer could love. But I almost say literally fell out of our seats when we lined up these images. Like they're different wavelengths, so not every star is visible in this image compared with this one. But like that star is that star. And this region here, that white circle, corresponds to the pixels where now sits the supernova. And the reason we almost fell out of our chairs was that these pixels here are extremely bright, meaning they're dark, meaning they're black, right? But they're very bright because this galaxy is over 200 million light years away. We were just crazy thinking, let's go see if a picture's been taken of it. It's pretty far away. But it had, and those pixels are extraordinarily luminous. If you actually do the calculations for the given distance of the object, if this is one star, it corresponds to a star that's over 1 million times the luminosity of our sun. And the reason that's so shocking is that no red supergiant gets that bright. They get to 100,000 times the luminosity of the sun. They don't make it to 1 million times the luminosity of the sun. The only stars that at any point during their lives make it to that luminosity are stars that are born with more than 50 times the mass of the sun. The real heavyweights. Okay, so what's wrong with that? It's a high mass star. It exploded. Two things. First, there was a prevailing theory that stars that are born that massive might not even explode. That implosion of the core that I told you about, the theory suggests maybe, people argue about this, but there is a prevailing theory that these real heavyweight stars, maybe that core implodes, the rest of this humongous star falls on it, and it just can't explode. All that mass is too much gravity, and the whole thing just snarfs into a black hole. Snarf isn't actually the scientific term, but I don't know a better one. So there was an idea that these really rare but extremely massive stars might just end their lives by going whoop and going out. No one's ever seen a disappearing star, but we haven't really looked very much because they don't get us as excited. An explosion gets your attention, but people are now, astronomers are now, starting to look to see if does any star just disappear on us. And there was a theory that the real heavyweight stars might just disappear. This one clearly didn't. It exploded. So that was actually the really exciting thing in my mind, was that such a heavyweight star, such a high mass star, is demonstrated here to have exploded as a supernova. Problem number two. Even these high mass stars, these super heavyweight stars, even if they do explode, they're not expected to explode when they're at their stage of life, when they're 1 million times the luminosity of the sun. They only get this bright during a fleeting part of their evolution, and that part of their evolution is supposed to be many hundreds of thousands of years before they explode. And so, A, we have a really high mass star exploding that many thought couldn't explode, and B, it's exploding at the wrong time of its life. We've seen heavyweight stars like this. There are some in our own galaxy. And the only times in their lives that they become 1 million times the luminosity of the sun is when they do this. This is a picture of one of those stars in our own galaxy. This is a very famous star. It's called Eta Carinae. It's thought to be 100 times the mass of the sun. It still lives in the center here. It's not dead. This was an eruption, not an explosion. But it's nearing the end of its life, but it's not thought to be at the end of its life. Back in the 1800s, the star was kind of an unremarkable star in the sky, and then it just sort of, and for lack of a better phrase, belched out all of this material. That's nice to come up with a better phrase than that. But it blew off. How's that? Many, many solar masses, many times the mass of the sun, out into space and enormously lit up and became the brightest star in the sky for a while in the 1850s. And now when we look at it, we see the remains of that eruption from 170 years ago flying out into space. And it's during those eruptions that they become 1 million times the luminosity of the sun, and only during those eruptions. And the theory of what stage the star's in is that it should be not near iron core collapse. It's in an earlier stage of its existence. So what do we have here? We have evidence from the luminosity that this is an extremely high mass star, and it exploded. Okay, so my colleague and I wrote a paper on this in the stodgy astrophysical journal where you write papers like this. And a lot of people, including us, were skeptical. How do we know this isn't just like a cluster of stars or something? How do we know it's one star 220 million light years away? Well, you know the answer. The next thing you have to do is get the final picture to show that the star disappeared, right? So we dialed up the Hubble Space Telescope after the supernova had faded beyond detection and say, could you please get another picture of it? And they did, and the star is gone. That's where the star was, and now it's gone. So pretty good proof that the star actually did explode as the supernova. So what does that do for you? It turns a stodgy astrophysical journal article into a Nature paper. All right, so we got 2 papers for the price of 1. Well, we got the second image there, and that's what did that for us. So this was cool. Now, what was most exciting to me, really, personally, was just that we demonstrated that such a high-mass star could actually explode and that it was doing it at the wrong time of its life. What it seemed like everyone else was really fascinated by, and I hadn't actually thought of this when we wrote the papers, was that right here, theory says there should be a black hole. Can't see it, right? But such a high-mass star does explode, but it's thought that the thing that's left gets at least pushed over the limit for a neutron star and eventually collapses down to a black hole. So in a very big stretch, we were the first people to watch a black hole form. I said it's a very big stretch. That didn't stop film crews, though, from acting like I was the first guy to see a black hole form. I didn't realize that's what they were doing until I watched the program and then realized, oh, that's why they kept asking me about black holes. So anyway, this is a little clip from a video I did after that. I don't own the sports car. They made me drive around in that. And then they, all day in San Francisco, convertible. And then they didn't get around to interviewing me till like 9 hours of driving around in this thing with them filming me. And by that point, I had a really bad hair day, so all the interview was, they didn't even let me comb my hair. So here's a little bit about that.
Was nothing. The star was gone. It exploded as a supernova and had now disappeared. And we think right there is a black hole. Right there. But I can't ever be 100% sure about that. Is that because you can't see it? Seeing nothing in black hole science is a great thing. You don't expect to see anything when you're looking at a black hole.
As images of black holes go, these few dark pixels are about as good as it gets. Without the death of a star, there'd be no reason to suspect there was a black hole there at all.
All right, so kind of a weird thing talking about seeing a black hole form because by definition you see nothing afterwards. Anyway, there it was. So at least in this one case, we were very surprised by what we found in the progenitor images. Leads to all kinds of questions. Do all really high mass stars like that explode? Do any of them just wink out and go away? Stay tuned. We're trying to answer those questions. Have me back here in 10 years or so, and I'll tell you what we've found. We've been searching and searching. But we've come a long way from our ancestors gazing up in wonderment at exploding stars 1,000 years ago. But in a real sense, I think their questions about what they were looking at have just been replaced by new ones. We know that what they saw was the explosion of a very massive star. But as we're finding out, nature still holds many secrets and surprises in store for us. And we'll just continue watching stars die just like they did 1,000 years ago. And with that, I'll take any questions that you have. Thanks.